Good morning. Today we'll discuss about one topic called the continuity equation. How to derive the continuity equation using different models of flow that we'll see today. And this is a topic which is in the subject called computational fluid dynamics. Myself, I am P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department in Institute of Aeronautical Engineering. So we have four models. First we'll consider the finite control volume fixed in space. Now, what is the basis of the continuity equation? As we have discussed already, it is based on law of conservation of mass, or mass is conserved. Mass can neither be created nor be destroyed. Okay, it can be transferred from one form to another form, or it can be transferred from one point to another point. It cannot be destroyed. Now, coming to the concept of the finite control volume fixed in space. So here this diagram is showing that. So what is happening is the control volume is fixed and the fluid is moving across the control volume. So the fluid is entering, the fluid is leaving the control volume. Now, at a point on the control surface, here at a point, the flow velocity is v bar. Okay, at this point the flow velocity is v bar, and the direction, the perpendicular to, if I draw a perpendicular at this point, that will be given by this fellow. It is a, you can say this is n bar, normal vector. This is a n bar, normal vector. Now the ds is the surface area of this elemental surface. Okay, this is a finite control volume. We are considering a small element, surface element, that is a ds. Okay, now if dv, okay, we are considering a small elemental volume inside the control volume, and that is a dv. So these two things we are considering. One is elemental surface and the other one is elemental volume. Mass conservation. What is the meaning of mass conservation? Mass can be neither created nor destroyed. It can be taken from one part to another part. Or the meaning is here, what we are applying is, if there is a change in the mass of the control volume, okay, if there is a change in the mass of the control volume, how that happens? It happens because of the difference in the mass entering and the mass leaving. Okay, if there is a difference in the mass entering the control volume and mass leaving the control volume, then only there will be a change in mass of the control volume. Now, what is that mass flux? So the mass flux is nothing but the mass entering the control volume or leaving the control volume per unit area. So that is given by mass flux. Okay. So instead of saying mass flux, what I said, the mass entering and mass leaving, to simplify the concept. Okay. Now the elemental mass flow across the surface area ds. Okay, this surface area is ds. Now the velocity of the control volume is v bar, and the normal is, here the normal is n bar. Now what is the magnitude of the velocity in this normal direction? It will be given by v bar dot n bar. The magnitude of this velocity in the direction of n bar is given by v bar dot n bar. Why we need this magnitude only? Because we are trying to find the mass that is leaving the surface normal to the surface. Okay, the mass which is leaving the surface or entering the surface normal to the surface. That is the reason we are taking this dot product, so that we get the magnitude of the velocity normal to the surface. So the magnitude of the velocity normal to the surface into the surface area into density, if I do the product, I will get the total mass, okay, entering or leaving that small control, the small surface area, okay, the elemental surface area which we have considered. The mass entering this surface area or leaving the surface area is given by the product of density and the magnitude of velocity normal to the surface and the surface area. Now what is the total mass? The net mass. So we have taken only small surface area. So suppose here only we have taken. So this entire surface is there. What is the amount of mass that is entering or leaving the entire surface? How to get it? If I integrate this elemental area mass over the entire surface, I will get the total mass out or going out of the control volume. So that is given by this equation. The surface integral of rho v bar dot n bar into ds. If you want to differentiate, you can put a bracket here. This is one term, the density. This is the another term, the magnitude of velocity normal to the surface, and this is the surface area. So that is one thing. With one concept we have derived what is the total mass leaving the control volume. If the total mass is leaving the control volume, then there is a change in the mass of the control volume. So how to get the change in the mass of the control volume? If dV, we have taken this dV here. If dV is a small volume inside the control volume, and if rho is the density of the fluid inside the control volume, then the product will give the mass of this small control volume. Okay, this mass of the small control volume is given by rho into dV. So if I want the total volume, okay, if I want the total volume of the control volume, what I have to do? I have to integrate this over the entire volume. So it is a volume integral. So the volume integral rho into dV gives the total volume of the control volume. Now what I need? I need the change in the volume per unit time, or the rate of change of the volume, or the rate of change, increase of the volume, increase of the mass, or decrease of the mass. Here increase is given, it can be increase or it can be decrease. If the net mass flowing out is a negative one, okay, so negative means the mass entering is more, mass leaving is less. So the mass of the control volume will increase. If the net mass out is positive, what is the meaning of that? If the mass entering is less and mass leaving is more, then the mass of the control volume will decrease. So it can be increase or decrease. So you can write the time rate of change of mass inside the control volume is this. Okay, this is the mass of the control volume, and if I apply dou by dou t, I will get the change in the mass of the control volume. So this is one, the change in mass of the control volume with respect to time. The other one is the net mass flow out of the control volume, that is given by this. So they must be equal, because whatever is entering, say suppose the net mass entering inside the volume is 1 gram, then the change in mass of the control volume must be equal to 1 gram. Okay, because the mass cannot be destroyed. So whatever is entering, it must be increasing, added to the mass of the control volume. So the net mass entering the control volume must be equal to the change in the mass of the control volume. So that is if I equate this one and previous statement, I will get this one. Now this actually this is the integral form of continuity equation. So if I put a plus here and if I put a 0 here, that is known as the integral form of continuity equation. Okay, so this is the integral form of continuity equation. What we need is a differential form and a conservative form. A conservative differential form is what is we needed. So what we are doing here, again we are applying the Gauss divergence theorem. What this Gauss divergence theorem says, okay, the surface integral can be converted to the volume integral if I differentiate the inside term. Okay, if I differentiate this integrand, what I will get? I will get the volume integral. So the surface integral can be converted into volume integral. So we don't have to get enamored by this divergence, rho, all these things. So what we are practically doing here is we are differentiating this fellow here and we are converting this surface integral to volume integral. So here it can be plus or minus. If this is plus, this is plus. If this is minus, this is minus. So both are equal. So what I have to do? I have to replace this surface integral with the volume integral. Why we are doing here? Here volume integral is there. If I put another volume integral, I can bring all the terms inside one umbrella volume integral and equate it to 0. So that is what I am doing here. So I equated to the volume integral. I brought this side, this one. What is the divergence of rho v? Divergence of V is del dot V bar. Now the divergence of rho v is del dot rho v bar. So that is the meaning of divergence of rho v bar. Now if I do that, what happens? What I am doing here? Here it is a minus 1, because what we are doing is here, yeah, this one. If this is a negative one, this will be a positive one. Okay. Now if this is positive one, that is negative. If I equate, I will get a sum here. The same thing here. What we are doing here, this plus this must be equal to 0. Now if I bring this differentiation term inside, okay, how we can do this at this rho dv, this is a small volume here, okay. The change in volume, mass of the entire volume must be equal to the change in volume of this plus change in volume of this plus change in volume of this, change in volume of this. So what I am doing, instead of differentiating the entire control volume mass, I am differentiating, I am finding the change in mass of this small volume and integrating over the volume. So that is the meaning of bringing this d by dt inside. So if I bring the d by dt inside, it will become dou by dou t. Okay. Now actually it should be dou t here. It is not a dt. Now dou by dou t, if I bring inside, it will be dou rho by dou t, and here it is a divergence of rho into velocity, that is given by del dot rho into v bar, and dv is common. The term with which we are integrating, this is volume, so it is a dv. Now this is the equation. Now this equation can be written like this. So what is this and what is the difference here? I mean, why we are making the integral into 0? Here the control volume shape is drawn arbitrarily. There is no particular shape. For the entire the integral over the control integral over the control volume to be equal to 0, the integrand must be equal to 0. So that is the concept. Since it is an arbitrary volume, arbitrary shape of the control volume, for the integral to be equal to 0, the integrand must also be equal to 0. So what I am doing, I am equating the integrand to the 0, and I am getting this is the what is called the conservative form of continuity equation. Conservative form of continuity equation in partial differential terms. It is not integration terms, it is a partial difference terms. If I expand this, I can write like this. So this is a one approach. We will see the other approach. Now what we are doing, we are taking a infinitely small or infinitesimal element. Infinitely small means infinitesimal element means infinitely small element. Okay. Infinitesimal fluid element means infinitely small fluid element. Infinitely small in the sense of the calculus. Okay. But it is a continuum. For that to be continuum, what it should be satisfying, the volume should be sufficient such that at any point of time there are some molecules always in the element. Okay, inside this element there must be always some molecules. Then only this can be treated as a continuum, continuous medium or continuum. Now here we are taken the Cartesian coordinates x, y, z. In x, y, z directions you have u, v, w velocity components, and this small one we are writing the velocities. Okay. Now this is positive direction, this is positive direction, this is positive direction. The velocity is u, the density is rho, the area normal to it is, what is this area? This is x direction. Normal to x is yz. So it is delta y delta z. Now rho u into delta y delta z will give the mass entering the left surface. Okay. Rho u delta y delta z will give the mass entering the left surface. Now is the density and velocity constant? No, there may be change in the velocity and density. So in which direction it is changing? It is changing with respect to x direction. Okay, in x direction it is changing. So the change of rho u per unit length, change per unit length is given by dou rho u by dou x into this is change per unit length. The total change is you can get by the length. Change per unit length into length, it gives the total change. So this is the initial rho u and this is the final rho u. Okay, into this perpendicular area delta y delta z will give the mass leaving the surface. So this is mass entering the surface, mass leaving the surface. Similarly, you can write in terms of z direction and y direction also. So now I have discussed how we got those things. We'll see the internal things. The transport due to such motion is often referred as advection. So if you any time come across the term what is advection, okay, advection means the transport of mass, okay, the transport of mass is advection here, okay. So what we'll see in convection, you know the term called convection. What is the convection means? It is the combination of conduction plus advection. Conduction happens between the surface and the molecules will carry the heat. The molecules will be transported from one part to another part. So the conduction plus conduction plus advection gives convection. So when this is a side point where we come across with the advection term. So that is what I told. Now coming to the main topic here, our topic, what is how to derive the continuity equation using the concept of infinitesimal element fixed in one place. Okay. Now, if m is the mass of the element, the rate of change of mass of the element is given by dm by dt. Now, this must be equal to the mass entering and mass leaving. Rate of mass entering and rate of mass leaving. That will give the change in mass of the control volume. So that is what is the conservation law. Now as I discussed on the diagram slide, the rate at which the mass enters the control volume, okay, is rho u into delta y delta z. The rate at which it is leaving is given by rho u into dou u by dou x of rho u into delta x into delta y delta z. So similarly, I can write in x y direction and z direction. Okay. Now, if I want to write in y direction and z direction, the amount of mass leaving, it can be written like this. Now, the mass of the element is the density into volume of the element. So the density is this rho and volume is already defined delta x into delta y into delta z. So density into volume will give the mass and the rate of change of mass is dou by dou t into rho delta x delta y delta z. Now what I have to write? I have to write what is the sum of mass entering and the sum of mass leaving. Mass entering minus mass leaving will give the change in mass with respect to time. So if I want to simplify here this rho u into delta y delta z is there, and here also one term is there. This is positive, this is negative, so this will get cancelled. Here rho v delta x delta z is there, and here rho v delta x delta z is there. This term also get cancelled. Rho w delta x delta y, this term and rho w will get cancelled. And we have a common term on both sides, delta y delta x delta z. Now this delta x delta y delta z we can eliminate because it is on both sides. If I simplify this equation, it will become like this: dou rho by dou t dou by dou x of rho u, dou by dou y by rho v, dou by dou z of rho w equal to 0. Now as we have already seen, dou by dou x of rho u, dou by dou y of rho v, dou by dou z of rho w can be written as del dot rho into v bar. So this is the directly we are getting the partial differentiation form of continuity equation in the in the conservative form. Okay, it is a conservative form and partial differentiation form. Directly we are getting from the concept of the finite infinitesimal, infinitely small fluid element fixed in space. The previous one, the finite control volume fixed in space, what we got? We got directly we got integral form, which is a conservative form. After manipulations, we got the partial differential form. Now we'll see the third aspect. What is the third aspect? The infinitesimal fluid element moving along the flow. Okay, the infinitely small fluid element is moving along the flow. So the velocity of this element is v and the volume of the element is dv. The mass of the element is always constant, and what is the mass? Mass is equal to density into delta x into delta y into delta z. Here there is no exchange of the molecules or the molecules between the element and the surroundings. In the case of the infinite small element moving with the flow, if it is infinitely small fluid element moving with the flow, then there is no exchange of the mass between the element and the surroundings. So whatever time may be, the mass of the element is fixed. So this is d by dt of m equal to 0. Now this is the continuity equation derived from this concept, but it is a non-conservative form. It is not a conservative form. It is a non-conservative form of equation. Now how to convert that into conservative form? So that is the task. Now this is delta v. So rho delta v. So this rho delta v I am putting here. So it will be equal to, so you can write this d and capital D both are replaceable, interreplaceable, because this is a substantial derivative and this is the total derivative. Okay. Now d by dt of rho delta v. Here two terms are there. I am differentiating partially. So if I do variable several, I am applying UV rule here. Rho and delta V are there. I am applying UV rule. If I apply UV rule, it will become like this. So this is the next equation. Now what I am doing, I am dividing this entire equation with delta V. Delta V is nothing but volume. So okay, this delta V, I am dividing this entire equation with delta V. So if I divide this entire equation, I will get this. So this delta will become here, come here, and here it will be only d rho by dt. Okay. Now we have seen what is this term while discussing the physical meaning of divergence. So what is the physical meaning of divergence here? The physical meaning of divergence is the rate of change of volume per unit volume. So this term can be replaced by the physical meaning of divergence. So d rho by dt plus rho into del dot v bar. So this is what we got. Now this d rho by dt. What is this d rho by dt? D rho by dt, if I want to, what is the rho? Rho is function of x, y, z and t. Now d rho by dt or d rho by dt physically there is no change in the meaning, only that the people apply, different people apply small d, and different people apply capital D here. Now what is this? This is equal to dou rho by dou t with respect to time plus dou rho by dou x into dx by dt plus dou rho by dou y dou rho by dou y into dy by dt plus dou rho by dou z into dz by dt. Now dx by dt, dy by dt, dz by dt, we all know it is u into dou rho by dou t, sorry dou x, and here it is dou rho by dou t plus v into dou rho by dou y plus w into dou rho by dou z. Now u, v, w, they are the constituents of, say suppose we have v bar is equal to u I bar plus v j bar plus w k bar. This is a v bar, and we have del rho is equal to dou rho by dou x into I bar plus dou rho by dou y into j bar plus dou rho by dou z into k bar. If I make the dot product of this one and this one, I will get this equation. So what I am doing, I am replacing this d rho by dt with dou rho by dou t into v dot del rho, v dot del rho. Now I have v dot del rho plus del rho dot v. If I combine these two, so it is nothing but the UV rule. UV rule I am applying reversely. So if I apply reversely like this, what I will get? Del dot rho v bar. So this is the final conservative form and differential form. Final thing we will see. This is the finite control volume moving with the flow. What is this? Finite control volume moving with flow. Finite control volume moving with the flow. Now the small volume, if I consider a small volume here dV, the mass of that small volume is equal to rho into dV. The total mass is equal to rho into dV volume integral, because we are integrating entire volume. The small volume we are integrating over the entire volume, so it will become volume integral of rho into dV. Now this is the if I differentiate this with respect to time, this is mass. The mass is conserved, means the rate of change of mass is equal to 0. So if I differentiate this mass with respect to time, then this is my continuity equation when I apply the finite control volume moving with the flow. Finite control volume moving with the flow. So this is the continuity equation. Now what I am doing, this small volume again, this small volume, the change in mass of the entire volume is equal to change in mass of the elements inside. So I am taking this differentiation inside. So I got this one. Now what I am doing, I am applying again UV rule here. Okay, rho is there, dV is there. I am applying UV rule. I will get this term and this term. Now if I divide this with dv and multiply with dv, I will get this one. Okay, what I am doing here, I am dividing this equation with dv and multiplying with dv, so that I will get this equation. So this one I am keeping it as it is. Now the term which is there inside this bracket, it is 1 by dv d by dt of dv. So this is nothing but the physical meaning of divergence. So I can replace this term with del dot v bar. So the surface integral of d rho by dt into dv, sorry, volume integral of d rho by dv dt into dv plus volume integral of d rho rho into del dot v bar into dv. So these two terms are there. Now what I have to do? I have to, as we have done in the case of the previous derivation, this d rho by dt can be splitted into dou rho by dou t into v bar dot del rho, and we also have del rho del dot v bar. So what it will give? It will give dou rho by dou t plus del dot v bar, or I can write rho v bar equal to 0. So this is our final continuity equation, which is a conservative form as well as a differential form. Here what we got is a non-conservative form and integral form. In the previous case, what we got was, initially we got non-conservative form but differential form, and finally we converted it into the conservative form. So from this exercise of doing the 4 models, what we can understand is, using any of the models, we can finally obtain the continuity equation in differential form, which is a conservative form. So that is about the continuity equation. So if I ask you to make it a 2-dimensional, I have to eliminate dou rho w by dou z. Okay, z direction if I eliminate, it is a 2-dimensional equation. If I make it a incompressible, density is not a variable. Okay, or density is constant. You can write density is constant. Density is constant means incompressible, as well as okay, it is not changing with time as well as space. That is the meaning of density is constant. It is not changing with time as well as space. So this is all the 3 places it is constant. I am taking out the constant, I am putting and equating. This is the 2-dimensional equation for continuity equation when it is a incompressible fluid. So with this I am closing the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.